It's great to be here this morning. I am a co-founder CEO of MemVerge, and I'm here to share with you about the big memory movement on behalf of both MemVerge and our partner Intel. So big memory computing is a new architecture of computing. It consists of an innovation in hardware pioneered by Intel in obtaining persistent memory. And I will go into more details in my talk. And it also consists of big memory software, pioneered by MemVerge with our memory machine software. And it's a combination of the hardware and software that has a promise of deliver memory that is abundant, that is low cost, and that is highly available. We believe that will have a fundamental impact to both the data center architecture as well as to all the applications in the world. So let me go into some details by taking a look at inside of a computer. And this could be any computer. This could be a server. This could be a PC. This could be an iPhone. When you look at any computing system, it has a computing unit, typically a CPU, where the application runs on. And then the data the CPU need to process are typically placed in main memory. And over the last 50 years, DRAM has been the primary media to power the main memory. And the main memory has a number of benefits. First of all, it's fast. It has a latency typical of 15 nanoseconds that allows low store operations for applications to run. So typically how you access the memory is simply assign a value to a variable or placing a data in a data structure, and it happens instantly. And you do not have to wait, and you do not have to do things asynchronously. But memory also has a number of limitations. And this is especially true as the audience here who are working in memory computing. Namely, it does have a limitation in terms of capacity. Typically, you have a few hundred gigabytes per server. It can theoretically go to terabytes, but the cost goes up exponentially as you increase the memory amount per server. And it is also volatile. That means if you lose the power to a computer, you lose the data that is placed in memory. So to complement memory, almost in all computing systems, there's a concept of a storage or external storage. And this could be a hard drive or SSD in your computer. And this could be a storage system in a data center. This also could be a cloud storage that's provided by a cloud service provider. And so typically for an application, if the data couldn't fit into a DRAM, or if the data you like to retain for the long term, you would move the data from DRAM to a storage system. And there are various protocols to do that. You can either using storage as block storage, as file storage, or as object storage. And no matter which protocol you use, storage I/O is incurred. And storage I/O is the movement of data between DRAM and storage. When you need to save your data into storage, you typically open a file or open an object or so on and start to serialize your data in your memory and turn them into on-disk format and then move them into storage. And more often, especially for data-centric applications, this data I/O is becoming the bottleneck. And this is not only in the physical movement of bits, but also in the software manipulation of data in order for the data to be moved between these two types of media. But today, there's really no other way because of the trade-off between DRAM and storage, where DRAM is limited by capacity, by cost, by its volatility, where storage can be much more scalable. You could have petabyte storage very easily now from many different vendors, either through hardware systems or through software distributed storage systems. It can offer higher capacity, much lower cost, and non-volatility, meaning it can survive power failures. And then on top of the non-volatility, various storage systems have built-in advanced data services, such as snapshotting, replication, deduplication, etc., to enable the space efficiency and high availability from your storage. But what you cannot overcome is the latency from the storage media. Even if you use the fastest type of storage, which is a NAND flash storage, you are still incurring tens of microseconds of latency, if not hundreds of microseconds of latency. And that is 3 orders of magnitude slower than memory. So when an application runs in today's architecture, it's also known as a von Neumann architecture, that you are incurring the performance penalty once the data goes into storage. You're also incurring the I/O that are data movement between DRAM and storage. And over the last 20 years or so, this is very familiar to the audiences here, because of the growth of data. And the growth of data actually happens in multiple dimensions, both in capacity, where it's becoming bigger, and in velocity, where it's becoming faster. That it is really pushing this infrastructure to be bigger and faster at the same time. And this is driven by a number of different applications that are emerging. These including big data analytics, especially the big data analytics of real-time data. This also including AI, machine learning, including real-time trading and analytics on capital markets, including HPC processing of oil and gas data, seismic data, genomic data, etc. It's also including movie making, when you need to making high definition 4K, 8K movies, and where you can only fit very little, 17 seconds of your movie into memory in order for the artist to process. So it's really stretching the limitations of this von Neumann architecture, where you need to place data between memory and storage. And people at Intel and people at MemVerge, we ask the question, why do we need to have these 2 different kind of media existing at the same time, even though that has been the case for the last 75 years of computing? But why can't we envision a world where you can have hundreds of terabytes available to your applications on your fingertips or in memory, so that your entire application data can be placed in memory? So this, not only you don't need to incur the latency of the slower storage media, but you removed the necessity of data I/O, or the movement between memory and storage of data. And this will be a very different world for how applications can be developed and how they can be developed as well. And this innovation is actually happening right now. And it starts with a groundbreaking new hardware that is introduced by Intel last year. This hardware is called Optane Persistent Memory. And this is a new type of memory media that is based on 3D crosspoint technology. And with this technology, you can achieve the performance at memory speed, namely nanosecond speed. The latency of Optane persistent memory is roughly around 200 to 300 nanoseconds for both read and write. And this is a bit slower than DRAM, which is about 15 nanoseconds, but it is fast enough to be used directly as a by-addressable memory media, where you can access it with load and store. And this is very different from using SSD as a swap or virtual memory, because in that case, you are not really directly accessing the SSD as memory, but you're actually moving it to DRAM before it's being processed. But with Optane memory as a memory extension, you can use it directly as bidirectional memory media. And at the same time, the capacity is bigger than DRAM. It's a different kind of physics than DRAM. It has the potential of reaching densities 10 times or more of that of a DRAM. And starting with the first and second generation of persistent memory, you can have up to 9 terabytes per server with the first generation of Optane. With the second generation, you can have up to 12 terabytes per server. And this will continue to increase as the future generation of our Optane memory is introduced. It is also lower cost than DRAM. The street price is roughly half per gigabytes of DRAM. And we expect this gap to increase over time as the next generations of memory being introduced as well. And most importantly, different from all the memories we have known in the past, or at least in the last 50 years that's popular in the servers, this memory is persistent, meaning it has the memory speed, but it can also survive power cycles. If you lose the power, the data will remain in memory. And this will solve one of the biggest issues with in-memory applications, whereas the data is not resilient to machine crashes or power failures. Where with this memory, now it is possible to building high availability capabilities so that in-memory applications, just like storage-based applications, can survive crashes and failures as well. So this is really a very different media that promise to bridge the gap between memory and storage and open up a new big memory computing architecture that will change everything in the data center. And so this makes possible the rise of this new architecture we call the big memory computing. And so what is big memory computing? You know, if you remember the picture before, you have memory on one side, you have storage on the other side, and you have all the data movement and the I/O in between. But in the big memory world, you have only memory. You have DRAM and you have Optane. So memory will become more heterogeneous rather than a homogeneous memory where everything's DRAM. Now you will have more than one kind. Intel was a pioneer that introduced the first of such new memory. And there will be other vendors who will be joining this market and delivering additional type of new persistent memory in the future as well. So this will become a multi-sourced new market that is being created. Now, as we mentioned, different kind of memory, they can all be used as bidirectional memory, but they do have slightly different properties. Optane memory is persistent, where DRAM is volatile. At the same time, Optane memory is slightly slower than DRAM, and so they require a new layer of software, where we call big memory software, that is really combining these different kind of memory and creating a software-defined memory that combines the best of all worlds between these memories, so that they can operate at DRAM speed. They can offer the combination of capacities between all these memories, and they can offer the average lower cost than what's available in DRAM today, and they can offer the non-volatility and delivering the necessary high availability services through software as part of this software-defined memory to the applications. And in this case, these applications could be in-memory databases, it could be data grids, it could be various kind of applications that are memory hungry, that where the capacity and performance of memory is the key bottleneck for these applications. And these big memory software and big memory computing infrastructure can really remove many of these limitations for these applications. Okay, so now let's look into the new hardware market that Intel has pioneered. So it really started last year. So it's a brand new market, a greenfield market that didn't exist before. I think this is IDC. On the left is a forecast from IDC. It started from 2019, with the initial set of customers. There were probably a couple hundred customers start using this new type of memory, and IDC is projecting a pretty dramatic growth over the next few years to reach $2.6 billion. This is only the byte addressable obtained persistent memory, as well as the other type of persistent memory that will join the market. It's a 250% growth rate over the last 3 years, and now $2.6 billion is great. 250% is great, but it's actually very small compared to the overall memory hardware market. The overall memory hardware market is about $100 billion. So this is about 2.5% of that market. So it has a lot further room to grow as well. So Forbes has made a longer term prediction of this new type of memory, persistent memory or PMEM, where it's predicting a crossover point in the year 2029, where there are going to be more persistent memory being shipped than DRAM at that time. And the market is expected to reach about $25 billion for persistent memory in year 2030. So this is a huge market in the making, from really zero in the first half of 2019. And as we mentioned, this is a great new hardware technology, a huge market in the making. It's going to benefit the applications all over the world, especially the in-memory databases and the in-memory applications. But there are hurdles for the adoption of this technology. Number one, the performance is a bit slower. Number two, to take advantage of the persistence as a memory, there's a new API. It's called App Direct that your application needs to write to. And the number of applications are doing that. But as we know, asking the application developer to rewrite their application is not always an easy ask. So 99% of the applications are not going to rewrite. And how do we get people, the developers and the operators, to adopt this new hardware? This calls for this new platform, new software platform we call memory machine. And that's where MemVerge came into picture. So MemVerge is a technology startup. We started about 3 years ago, co-founded by Shuki Brook, Yuan Li, and myself. We have been working in the infrastructure space, both in building fast storage systems as well as building virtualization systems. And as we see this new hardware coming to market, it reminds us of the days 20 years ago when another hardware transformation took place. And at that time, it was a multi-core CPUs. And when the CPU are reaching the clock speed limit, where each core cannot go any faster, the architecture start to go horizontally to multiple cores. But applications have trouble adopting it because applications were written not for so many cores. So the threading model really couldn't take advantage of all these cores. And as a consequence, the server utilization start to go down. And on a server, typically 5% or 10% of CPU time are really being utilized. And that's a big waste for the data center. So the solution to that was you either have to rewrite your application, or you could introduce a virtualization layer that abstracts the new hardware so that you don't have to rewrite your application, and yet you can utilize all the cores. And at the time, that was exactly what happened, the latter. And a company called VMware emerged, and creating a new encapsulation called virtual machine that allow multiple applications to coexist without rewrite on the same server, so that all these cores can be used. And then it gradually added more capabilities into that virtualization layer and growing to a $10 billion plus new software market. And we are looking at a very analogous situation here, where this wonderful new hardware that are emerging, and it has new features that does require the applications to rewrite to take full advantage of it. And for the applications that are not ready to rewrite, there's room to creating a new memory virtualization layer that virtualizes the different kind of memory and deliver them in a new encapsulation of memory that is software-defined memory that is hopefully bigger, cheaper, and as performant as the DRAM they're used to before, and deliver this all without application change. And this is what we at MemVerge have worked on over the last 3.5 years. And we shipped the first version of Memory Machine, this new layer of software, last month on September 23rd. And what it delivers is exactly what I described. It can deliver all of the memory, the combination of DRAM, and obtain up to 9 terabytes for a two-way server to the applications, and it delivers them in software-defined memory machines. Each of these can have dynamic configuration of DRAM, PMEM combinations, and you can dynamically change the ratio between the DRAM and PMEM so that you can achieve the best trade-offs between performance and cost. And for all applications, we can find the right combination that delivers a DRAM level performance and at the same time deliver a memory cost saving anywhere between 30% to 50%. And not only that, we also start to building advanced capabilities into this software layer. And the first of such advanced data services we deliver as part of software-defined memory is something we call Zero I/O in-memory snapshot. And this is a new feature that is only possible when the memory is persistent. Because the memory is persistent, this allows us to capture the entire running state of an application. For example, if you're running an in-memory database, the entire database can be captured without incurring I/O. So before the existence of this Zero I/O in-memory snapshot, a typical method of saving in-memory application or in-memory database would be have some in-memory mechanism to checkpoint the database and move them into a storage system. And this is increasingly time-consuming and disruptive as the application and database is becoming bigger, become hundreds of gigabytes or even terabytes. It will take minutes, if not hours, to completing such I/O-intensive checkpointing process. But now when the memory is persistent, even though our memory service to be compatible with DRAM is volatile, but because the underlying media is persistent, we can instantly capture all the data that already running those memory and just remember those pages so that those memory states are kept. So this incurs minimal interruption to the application, typically less than 1 second, even if you have hundreds of gigabytes of memory there. And this also can allow the application to continue to run without impacting the integrity of the memory pages that were captured in the snapshot. And we also learned from the snapshotting algorithms that are typically found in storage systems, and we reinvented those for memory, which is a much faster media. So it's a very challenging technical task that we were able to complete over the last 3 years. Is we were able to do the copy and write between these memory pages that allow you to take sequence of these snapshots, up to 128 of them. And while we are capturing only the deltas, so only the memory pages that have been changed, that we create additional new memory pages for. And this gradually, this dramatically saves the amount of overhead these snapshots will take in your memory space. So what this essentially created is a time machine where you can roll back your applications to any of the previous snapshots. So if you made a human error, if your database is corrupted in any reason, they can roll back to the last no good snapshot of your database. This would also allow you to have quick recoveries from crash, and that's actually one of the first use cases that we have. The last snapshot will automatically you can automatically recover your database or your applications to the last good snapshot. And we can also enable cloning capabilities. So if you have a in-memory database instances running, based on those previous snapshots, we can create additional instances without physically replicating on memory. Because through our virtualization, we can map multiple logical memory spaces to the same physical memory spaces. This allows you to quickly and resource efficiently creating additional instances of your in-memory applications on the same server. And this would also allow you to move these snapshots once they are taken to other servers, even to different data centers, or from on-prem to cloud, and providing another way of moving an application instances by moving these memory machine instances from servers to servers and from data centers to data centers. And most wonderfully of all, that we can do all these without application change. So the application is not even aware, is blissfully not aware of all these things happening in the infrastructure. And we are providing all of this in a compatible interface to the application, and they think they are still using DRAM. And all this is managed through our GUI or our COI or our API by the operator, and while the application continues to run as before. So this is a new abstraction layer that we have created that can really take the best of both worlds between DRAM and Optane and deliver them in a wonderful new way, how in-memory application can run on in a data set. Okay, so as you can see, I'm pretty excited about this technology. We were heads down developing this, and I think this has the potential of changing everything. Just this combination of this new wonderful hardware and this new software layer. And a number of customers agree with us. Over the last year, we have been working with a couple dozens of alpha and beta customers, and the early adopters largely belong to one of these three verticals or three industries. And these are just the first three industries that are embracing this. And we believe over time, this has a broad applicability to almost every industry in the world. But let me give you some examples of the first use cases that we have been working with some of the cloud service providers in lowering the cost of their memory infrastructure without sacrificing on performance, so that they can fit more virtual machines and more containers per server in delivering their cloud services and reducing the cost per VM. We have been working with both the movie studios and banks and hedge funds and stock exchanges to really enhance their in-memory infrastructure, both for the movie editing software, for the in-memory databases, and other in-memory applications that financial services use. And by not only delivering larger memory, therefore, they can fit more of their movies and more of their market trades into memory, but also we offer very fast crash recovery, so that if a creative artist managed to crash their movie editing software, which maybe not so surprisingly happen quite often, as those artists are very creative, or when the server crashes in the middle of the day while trading is going on, and where all the data in that in-memory database is only in memory, and therefore you lose hours of time to recover this database from the logs. That our software can reduce those hours into minutes or seconds, so that the downtime can be much reduced, and there are millions of dollars being saved in both of these use cases. And now let me just show you some details of some of these early use cases. First is for the cloud service provider. This is a low TCO, bigger memory, no performance loss use case to reduce the cost per VM. So on this chart, with the orange bar is you're running KVM on DRAM, and this is without us. So orange is the baseline, we test various applications, just making sure we can deliver the performance that are similar to the baseline, so that while they can achieve the cost saving, in this case about 30% cost saving, and without losing on the performance front. And this is one example of such application, which is running MySQL. MySQL database running Sysbench query per second. Running a DRAM, you're looking at 47,000 ops or transactions or queries per second. Where if you move into our software, so all the green bars are running our software. And as I mentioned, you can dynamically configure the ratio between PMEM and DRAM. When the entire VM running on PMEM, the performance is about 20% slower. And this is understandable as the underlying persistent memory is a bit slower, and therefore it reflects in the application performance, and in this case, about 20%. Now, as we start increasing some DRAM to the mixture of our software-defined memory, that our performance starts to increase. And when we add 16 gigabytes of DRAM, the performance actually exceeds the performance of DRAM. And this is surprising, pleasantly surprising. And you might ask why? Why would the combination of PMEM and DRAM, where PMEM is slower than DRAM, give you a performance faster than DRAM? The reason is that we are bypassing the OS in handling memory allocation and, of course, memory tiering between these two types of memories. And we have applied a number of software optimization that are more aggressive in optimizing for data-centric applications. And therefore, in this case, we are more aggressive in using huge pages. We are more aggressive in doing some other optimizations, and we are pretty optimal in tiering by having configurable tiering algorithms between PMEM and DRAM, so that for all cases we can get performance close to DRAM, either slightly higher or slightly lower, and for some of the applications such as this, we can achieve performances even higher than DRAM. So that was really good to see for both us and for the customers. And we are really in a late stage of testing with our customers in moving this into real production use for them. Okay, so this is the first example. The second example is using our Zero I/O in-memory snapshot to enable crash recovery and crash protection for in-memory databases, or in this case, in this example, are using Redis, which is an in-memory key value store. I'm sure all of you are familiar with it. It's a very popular key value store, very simple, very fast, stays in memory, and it also has some nice mechanism, RDB AOF, that allows you to capture the in-memory state onto storage system so that you can recover from it as well. But that does take time. Understandably, storage is slow. So in this case, when you have 300 million keys, 350 gigabytes, it takes about 15 minutes to recover the Redis instance from storage system back into memory and start running again. Now, if you use us, if you use a MemVerge memory machine using our snapshot, the recovery takes half a second. So it's a very dramatic difference, because all the data are already there on persistent memory. We just need to set it up so that it becomes running again. So this is really 1,500 times faster. How we can, using this in-memory snapshot mechanism, we can have much faster loading and recovery of a database. Okay, and so you can see how this is applicable to those financial and movie makers, as well as the other applications where we can be much more available for those applications. Now, let me go into the third use case. which is AI machine learning use case. And these numbers are from our collaboration with image recognition, facial recognition company. And this is for their inference mechanism, where they have a model where you have trained and you are doing the inferences from, but they also have various feature libraries where they need to use as part of their inference. And when without us, without Optane plus memory machine, when everything is in DRAM, and you couldn't fit in DRAM, so then they use MongoDB and so on SSDs to store the overflow data, the extra feature library. And that's the orange bar. So where you see the transaction per second on the left-hand side, and the inference latency, and the unit there is microseconds. So you'll see the orange bar where the transaction is relatively slow, the latency is relatively long. Where with the green bar, once you use memory machine where we're delivering larger memory, and we solve this DGM problem, data greater than memory problem, with our big memory solution. The transaction increases about 4x, up to about 4x, where the latency decreases about 100x. So you can get much faster throughput and even faster latency for the facial recognition application in this time. So that's another use case that we're working on. We're starting to work on with some other customers and partners in the artificial intelligence machine learning space. All right, so to summarize, I think we are looking at a brave new world here, and I think this is great news for the in-memory computing industry, where from infrastructure through the combination of this new breakthrough in hardware, Intel Optane memory, and this new layer of virtualization software in memory machine, that we can have various of applications start to running on top of it and utilizing not gigabytes but many terabytes of memory, and having that as disposal in your disposal to power your applications. And we can deliver this memory not only at DRAM speed, but offering advanced in-memory capabilities such as snapshotting that was not possible before. So you can make many new things not possible before become possible in the future. And we are very proud between Intel and MemVerge to be the purveyor of this new technology, where we hope that we can help open the door to this new world of big memory, where the memory is abundant, is persistent, and highly available. So thank you for having me here, sharing our excitement with you, and feel free to contact either of us at Intel and at MemVerge to learn more about big memory, and we look forward to the collaborations. Thank you.